Hi everyone, in this session I am going to be explain the graph coloring problem. So graph coloring problem is nothing but assignment of colors to the either vertices or edges of the given graph. Here the condition is no two adjacent vertices or edges have the same color. So the graph coloring is possible for either to color the vertices or to color the edges. If there is no particularly specified, then by default we are going to be consider the problem is the graph coloring of vertices problem. So the graph coloring problem is generally seen as two types. Whether the first one is whether it is the M coloring decision problem. M coloring decision problem is nothing but, or M coloring decision is nothing but, we have two inputs. One is the graph, second one is the number of colors. So we are going to be say the answer as we didn't color the graph. The given graph is possible to be colored with the given number of colors or not. Only we are going to be say that answer. That means it has the two outputs. Either if possible answer is yes, if not possible answer is no. So this is about the M coloring decision problem. And second one, second classification, nothing but the graph coloring may be fall into either M coloring decision problem or second one, M coloring optimization problem. M coloring optimization problem is we have the only one input, that is the given graph itself. Output also only one. We are going to be saying the minimum number of colors needed to coloring it. The minimum number of colors needed for graph coloring, that is our output. So in generally the graph coloring problem, either the decision problem or the optimization problem. And also in generally particularly in our examination we are going to be get the question from M coloring decision problem. Nothing but the examiner gives us the graph and also gives us the number of colors. Okay, we are going to be find how many possible ways are there to coloring that graph. If at least we find the one solution, our answer is yes. And if it is yes, if it is yes, we try to print all possible solutions. Print all possible solutions. So that's why the graph coloring problem fall into the algorithm designing technique of backtracking here. So because we try to find all possible solutions. So this is about the graph coloring problem statement. Now we are going to be consider one example. So the number of vertices are 4, in general labeled as 4, n, sorry, in general labeled as n, and the number of colors for this graph is 3. How many colors? We have 3. So in general labeled as M. So the color labels here, don't try to fix with the color name, better to go with a color label. So when we have the 3 colors, so I am going to be fix 3 color labels. The first color label, second color label, third color label. So you can choose your convenient name for that color. So for this graph I am going to be construct the state space setter. So when you are talking about the backtracking, edge talks about the solution vector, not the state. So maybe in dynamic programming, state talks about solution, but here edge talks not the vertex or state. So this is the first vertex possibility color. First vertex I may be labeled with a 1. I colored with which label? 1. So when I labeled for 1, then I only think about the second vertex. So I hope you are good at the backtracking general approach. Backtracking kth vertex coloring is possible if and only if when the k up to k minus 1 is colored, then only we have the right to think about kth vertex. So when I am going to be think about the second vertex, that means already first vertex is colored. Now I am going to be check it. So what is the second vertex color? I must have tried all possibilities. So that's why I am going to be go with a first label. So that is nothing but 1. So when I consider the second vertex label is 1, color label is 1, I am going to be check it first whether it is a legally nothing but valid color or not. How I going to be decide whether it is a valid color or not? So I am going to be consider the solution vector also. Like I have the solution vector x, vector size is the number of vertices. I colored the first vertex. What is the label I assigned? 1. I am going to be thinking about the second one, nothing but the 1. So when it is considering about the 1, I must be think whether it is a valid or not. How I realize whether it is a valid or not? Because I have the cost matrix and I know which vertex I am talking. So this is my vertex like I, or maybe labeled as kth color, kth vertex. I am going to be check which vertices are already colored. Those from those two, the kth vertex, is there any edge or not? If there is an edge, then only the adjacent vertices not having the same color. So that's why I don't know how many vertices are colored, but I know particularly with a label or variable k minus 1 are colored. So that's why I am going to be use one more indexing variable I is 1 to k minus 1. I am going to be check with k to I, is there an edge or not? My dear, this is not the weighted, this is the adjacent cost, it is the adjacent matrix, not the adjacent cost matrix. So that's why if there is an edge, automatically this value is 1. In other words, not the 0, both are the same, because in the adjacent matrix we have the only 2 values. If there is an edge, direct edge, value is 1. If there is no direct edge, value is 0. In the same way, k to I am going to be considered if not equal to 0. Yes, that means there is an edge. If there is an edge, then I am going to be check one more condition. What is that condition? What is the solution vector of that I is same as the solution vector of k. There is an edge, yes, 1, 2, 2. What is the one color label? 1. What is the second color label? 1. Is it possible? No. So that's why if it is possible, I am going to be check, then go for the next color. So when I go for the next color, then I am going to be initialize my solution vector label as 0. Initially all are the 0. Now when it is initialized with a 0, I am particularly talking about x of 2. What is the initial x of 2 value? 0. So then I go for the 1. If 1 is not possible, then go for the 2. If 2 is not possible, then go for the 3. 3 is not possible, can I go for the 4? No, because I have the only 3 colors. So that's why here we are going to think the proper logic based on using basic mathematics. X of k is nothing but k plus 1, x of k plus 1, nothing but already some value is there. From for that value we are going to be add 1, so that is nothing but x of k plus 1, and I can't go with infinite. I must be end with 3 only because I have the only 3 colors. So that's why this value modulus, or better to write modulus with, I hope you are good at the modulus operation. 4 modulus is the 3. 3 modulus max remainder is, modulus always gives us the remainder. Nth, what is the max remainder? N minus 1. But how many colors we have? 3. If I consider the 3 only, what is the maximum I am going to be get? 2. So nothing but it allows only 2 colors, but I have 3 colors. So that's why I am going to be considered 3 plus 1. I am going to be generalize this one. 3 is nothing but the number of colors labeled as M. So that is nothing but M plus 1. So this is the simple logic to update every time. If the color is not legally valid, then go for the new color, and you want to find all possible solutions. So that's why you can update x of k is nothing but x of k plus 1 modulus M plus 1. So when it is not possible, then simply I go with a x of k plus 1 modulus M plus 1. I will update. So that means when 1 is not possible, then I go for this 2. And in this logic, once you reach the 3, what about our next value 4? What is the 4 modulus 4? 0. So that's why that indicates all colors you have verified. So now I go with the 2. So I am going to be check. So 1 is fail, 2. Yes, 1 to 2 n edge. What is the 1 color? 1. What is the 2 color? 2. Then I go for the 3. So once again I am going to be check with the 1. What is the 3 edges? Vertex 3 adjacent? Only 2. What is the 2 label? 2. What is the 3 label? 1. No problem. Then I go for the 4. Vote for with 1. What is the 4 adjacent? 1 and 3. What is the 1 color? 1. Not possible. I go with the 2. What is the 4 adjacent? 1 and 3. What is the 1 color? 1. What is 3 color? 1. No problem. Nothing but 1 2 1 2 1 2 1 2. This is a solution. Then I not satisfying. I want to find all the possibilities. Then what I am going to be do? I can be increment the last vertex. Which vertex you have recently added? 4. So I go with the next one. What is the 2 plus 1? 3. 3 modulus 4, 3 only. So yes, that is also one possible. Then I go for the not satisfying. I go for the next one. 4 modulus 4, 0. 0 indicates not possible. All colors you have verified. Then take the backtrack. You are at this node. So then what is that path? 1, 2, 3 visited. Then what is the 3 colors for the vertex 3 as of now? Considering colors only 1. Then I go with the increment by 1, 2. So is it possible with the 2? I am going to be check it. No, because 2 and 3 are adjacent. So then go with the 3. So possible? Yes. Then once again here I must be go with a 1. 1 is possible? No. Adjacent. 2. 2 is possible? Yes. Here the color is 1, here the color is 3. No problem. I find the one more solution. So then I go with a 3. 3 is possible? No. 3 is the adjacent. 4 to 3 in adjacent. What is the 3 color? 3. What is the 4 color? 3. Not possible. Then increment. Then which becomes 0. All color verify. So then I take the backtrack here. So as of now I have verified 1, 2, 3. Then I go for the next color. Next color is nothing but 3 plus 1, 4. 4 modulus 4, 0. I have verified all the colors. Then take the backtrack. So the second vertex I go with the next color. Like this is the repetition procedure to find all possible solutions. These are all the possible solutions to find the different possibilities of coloring the vertices with the 3 colors. So this is about the graph coloring. Now try to find what is the algorithm's time complexity. My dear, the basic mathematics, these two formulas, this one and this one, based on those only we are going to write our algorithm, this one. If you are clearly observe, what is the time complexity? For the first vertex, I have the, so the time complexity is For first vertex, how many possibilities we have? 3, nothing but the m. For the second vertex, the same m. Worst case I am talking. So that means how many nodes we have? N nodes. Each one produces another possibility, nothing but into, not the place. M into and so on. How many times? N times. Nothing but. What is the time complexity for the worst case? Order of m power n. So this is about the graph coloring problem using backtracking. Thank you.